And I lost your last recording, so I must make it. So we can see that this formula is going to become important, but also applying it to the actual graph or the actual original formula is important as well. So this is applying to just f of x, and this is applying to the specific function if we were working with parabola. Why must that half be inside before being squared? Why must that half be inside before being squared?
Because it's part of the X translation,
Yeah,
or
that's right. If it was outside, it would become a y transformation. So by keeping it inside whatever's happening to x, it's clear it's an x transformation. Now we're going to move on to a slightly harder thing. We're going to take our same formula, and now they just give us a graph. Ah,
I
no.
hate sine curves.
Ah, I love sine curves. You know why I love sine curves? Because they
Why?
represent tons of things in nature. So the very
Like electricity?
electricity, sunlight, um, radio waves, frequency,
Okay,
photons, solar flares, waves, sound, earthquakes. But also, let me tell you this: when you find something in science that matches the natural world, that tells you you're on the right track. So it's like, holy cow, the natural world operates in this way that happens to be mathematical. That's useful. So when you can suddenly imitate the natural world, you can solve a lot of the problems. So if you can invent easy energy, all the problems we're facing now. So let me ask you this. What's the period of a normal sine curve? Let's look at a normal sine curve.
360.
360 is the normal period. What's the normal amplitude?
1.
1. What is the normal, what am I going for here? No, that's pretty good. What is the axis
Of what?
of a normal sine curve? In other words, what does it rotate around? What line, horizontal line, would you see equally right in the middle of it?
0?
Okay, let's look. Let's go back and study our sine curves. Where would you say is the? Oh, yeah,
Sine curve.
yeah, it is a sine curve. So, what would you say is the line right here that goes right through, that it's all symmetrical about? This line right here.
Oh, okay. What?
That's the x-axis, right?
Yeah.
What's the mathematical formula for the x-axis?
Zeros.
No. All formulas are y is equal to something or x is equal to something. So
Y equals X.
no, here's y is equal to x. It's a straight line. If I were to zoom in, it's a normal line. So
Oh,
I'm trying to find a formula for a horizontal line at right there. And I'll let you in.
X equals Y.
Okay, x is equal to y is still just a straight line. It's just you put
Oh,
the x first. So what happens if I do x is equal to 3? Or sorry, y is equal to 3. What is that? Let's draw red line. Oh,
Y equals 0.
yeah, there you go. The horizontal x-axis is the formula y is equal to 0. So that's the axis, right? Notice it's what's the max value on the y-axis here? What's the max value?
1.
1. What's 1 minus 0?
1 minus 0 is 1.
So we determine the amplitude by taking the max, subtracting the min. So we can determine we've determined the axis is y is equal to 0. How would we find the max? Well, we would take the max or the amplitude. Amplitude is equal to max y value minus the axis. In this case, it's 1 minus 0, which is 1. How would we find the axis? Well, we take a max value and we add it to the min value and we divide it by 2. So the
Not
distance,
just the midpoint.
that is the axis. So what is the max value of a normal curve? The max value is 1. The min value is minus 1. Add them together.
1
1,
minus
1 plus
minus
minus
1.
1. 1 plus minus
Oh,
1.
1 plus minus 1 is 0. Divide by 2 is 0.
Oh, suddenly we get the axis. Y is equal to 0. So the axis is equal to the max point. And you might say, well, that's useless because I know these from the thing. Yeah, but these are all useful when we transform it. Now we got to look at this red graph over here. Now we got to look at this red graph. We got to figure out let's focus on these. We got to figure out its max point, its min point, and its axis, especially if we want to figure out some other things. Or we can just use the formula once we find the max min point, and it would help to know the amplitude. So now let's look at this red graph and figure out some things about it. So there's the max point of the red graph. Would you agree?
Yeah.
That's the midpoint of the red graph. Would you agree?
Yeah.
Can you tell me the max point of that red graph? On the
One.
y-axis? Yeah. Max is 1. What's the min?
The min is -5.
Okay. Can you look over at some of these formulas and maybe figure some stuff out for me? So tell me what you want to figure out and go for it.
Let's figure out well, we already did the max and minimum.
Yep. So what can we figure out in here?
Oh, we can figure out the axis.
Okay, let's do it. Tell me what I do.
1 minus -5. So
Careful. This is the formula. So we're going to actually put max in brackets, and we're adding. It doesn't say minus. And I know,
right.
I know what you're saying, and you're right, but I want you to use this method. Divided by 2. So my max is what?
So 1 minus 5 is -4/2 is -2.
So the point I wanted to get.
What? Why are you laughing?
I wanted you to say plus -5, which becomes -5. I don't want you to just skip to -5 because it's important to apply the formula. Okay. So you get -4 divided by 2. What do you get?
-2.
So that means the axis in this one is y is equal to -2. Let's have a look. Is that -2 on the x-axis here? On the y-axis?
Yes.
Does that look like it's the axis?
Yes.
Oh, did you get it?
Yes.
So we should mark it down, no?
Yes.
That's why I'm laughing.
I don't get it.
Always mark down because it's hilarious. Yes. Yes. Okay, so you figured out this. Is there anything else you can figure out? You figured out this. We can just get rid of it. Anything else you can figure out?
It's okay. I gotta get this screen out of my face.
So you got this done. This is done.
Okay.
So
we got axis, max, minimum. Let's get the amplitude.
Okay, so the amplitude says we take our max value and we subtract our axis.
Yes.
What's our max value?
Our max value is 1. I mean, yes, it's 1. 1 minus 2. So we get -1 as our amplitude.
And that's why I didn't want you to do it like that. So, what's the formula? It's max minus axis. We open the bracket. What was the axis that you found?
The axis we found was -2.
Oh, look at what I've written here. I've used the formula. There's a formula.
Minus. Oh, so 1 plus 2
There's a
equals...
formula rule, and then there's a value, which is why I wanted to insist that you do it this way. Okay, go.
The amplitude is 3.
Thank you, sir. Thank you for...
No problem.
Yes, much appreciated, which makes sense because it's quite clear. If I draw a little amplitude here, it goes up by 3. Guess what? By the way, the amplitude is also here from the min to the max, or min to the axis. So you could take it as well. You could also add the two values of them, and I believe it's actually you subtract the max and the min and you divide by 2. But this is a much better way, I feel. It's less complicated. But you could take max minus min and divide by 2. How about you try that for me? Max. What's the max?
All right. 1.
1 minus.
1 minus -5.
No. Yes. My bad.
Yeah.
Yes, you're correct, and I was wrong. Okay.
Mm-hmm.
What's 1 minus -5?
1 minus -5 is 6 divided by 2, so you get 3.
And is that the amplitude as well?
Yes.
So we discovered that the amplitude can also be determined, if we don't know the axis, as max minus min divided by 2. Does that make sense?
Yes.
Useful. So now my only question is, I need to figure out some period. What's the period of a normal sine curve?
The period of a normal sine curve is 360 degrees.
Does this red look like it's got a longer period?
Yes.
Yeah. So we need a clean graph maybe. So let's see if I still have a clean graph. Yeah, I do. So let's make a clean graph and find out several useful ways to find a period on a graph that's uncertain. To do this, we need to study our parent curve. Would you say that this is the start of a sine curve?
Yes.
And this is the end?
Yes.
So that's one way of how far was the, is it from here to here?
360.
Right. How far is it halfway? 0?
180.
So if I knew the halfway point and doubled it, I would find the
Period.
Yeah. What about here? The quarter way, we always reach the max point. If I took the quarter way and multiplied it by how much, I would get the period.
Yeah.
If I went to the quarter distance, how much would I
You
have?
multiply by 4.
Oh, so we have this weird connection because at the quarter mark it reaches max, doesn't it?
Mhm.
And then at the halfway it reaches back in the middle, doesn't it?
Yep.
So if we know the halfway, we could double it. If we know the quarter way, we could quadruple it and come up with the period. Another interesting point is at the 3/4 point, it reaches the min. Right?
Yeah.
And then finally at the end, it comes back 4. So all sine curves look like they can easily be equally divided into 4 separate groups. If we see this pattern, we can study and evaluate any sine curve. So if I know the peak value, now I also want you to notice this.
What are you doing?
What is the value right here of the x value of this max point?
90.
What is the max value of this x point?
450.
How far are they apart? How do you determine how far apart something is?
It's 90 times 5.
No, I want you to use the number 450 and tell me how far apart 90 is. If you were, okay.
All right, I'm going to subtract it. And
Oh, there you go. Thank you.
I can
90 times 5.
I don't recall ever saying that. It's 360.
Oh,
apart.
so the distance between two max points is the same as the period. What's the distance from here, 630, to this point, 990?
306.
Oh, so the distance between min points is also the period. So that's several ways we have of finding the period. Now I want you to look at this graph here, right there, and focus on the red graph and see of the many methods that we have determined if you can figure out the period of this red graph. It doesn't finish properly, so that's hard. We know its axis is right here, but it doesn't quite finish for us, so it's kind of hard to figure out. Tell me a method we could find the period of this red graph based on what we just talked about.
Let's see if I'm trying to find a good point first.
Yep.
Oh, 540. So 540 is here.
Yeah, 540 would be what? The min point down here?
No, I was looking at the one on the left side.
Negative 540 right there?
Yeah.
Yeah, okay. Negatives are
And
hard to
then-
work with, but you could do it.
And then yeah, I was gonna go there.
So it looks like these are, 3 of them are 270. So one box is how much? If 3 boxes are 270, one box is how much?
One box is 100.
So if 3 boxes, if 3x is equal to 270, 1x is equal to what?
270 over 3. 90.
So that means each horizontal box here is 90 degrees. And it looks like you're trying to get here. How many boxes is that?
180.
Ah, so that's 180. How do I find the distance from 180 and minus 440?
180 minus 540.
Ah, careful. The distance is minus whatever the unit is. What's the unit? That's a formula. That's why I always encourage you to use brackets. This is the formula, point A minus point B. Point A is 180 minus what's point B?
minus 540.
Oh, so it's 80, sorry, 90, not 80, 90 minus 540. Yeah, you can use your calculator. 90 minus.
720.
Oh, so it looks like the period of this is what?
Looks like the period of it is 720.
Oh, and how much more of 360 as a multiple is 720? What would I multiply 360 by to get 720?
To find 2.
2. Great. Let us look at what happens. What goes in front of a sine x to change a period? If I put a 4 in front of this x, whoa, that sine x, that period got smaller. If I put a quarter in front of that sine x, holy cow, oh, it didn't even do it properly for me. So I'll do it like that. It's like, holy cow, the period looks like it's gotten bigger. What would I put in front of my sine x to make it 360, to make it 720? What would I put in front of my x here to make the period 720?
2.
Let's try it. Uh-oh. Looks like my period's 180. You're right.
3.
I wanted to. Oh my God, now you're just guessing, and I can tell. 2, I know it's something related to 2, but it looks like 2 didn't do it for me. What am I doing wrong? I remember Peter used to tell me X transformations do the opposite of what I want. I want to stretch my period by 2.
Yes. So if you multiply by x, you're actually dividing by x.
Yeah. So if I have X here, what do I put in front of it? I don't, instead of multiplying it by 2, I want to multiply it by,
1/2.
yeah. Let's see if you got it. Is this period 720?
Yes.
Boom. What did you tell me the axis was? What did you tell me the axis was? Let's go back to our formulas. What's my new axis?
I said that the axis was -2.
Yep. Now, where would I find an axis in the formula of f of x is equal to a times, or let's make it g of x, times f of k, x minus d, plus c. Where do you think the axis is on all that? Let's have a look at a normal sine curve and see what happens. Here's a normal sine curve, right? Agreed?
Yes.
Here's the normal axis, agreed?
Yes.
Let's lower this by 2. Whoa. What do you think I should
So
do?
that means that the axis would be at C.
Yeah. And you determine and what happens if I lower it by 3 or raise it by 3? Let's see if I
Axis is 3.
Yeah. So it looks like this value here is directly related to axis, and you determined that the axis was what?
I determined that the axis was -2.
So that means if I take my little formula that I'm working on down here, sine of a half x, and I subtract 2, did I get the right axis?
Yes.
Oh, so far so good. Now I just got to figure out, so far I figured out k, and I figured out c, right?
When did we figure out K?
Well, that was the
Oh,
half.
1. Yes, right. Yes.
K is the flip of whatever you want to do with it. So whenever you figure out,
the amplitude. I know where we could.
where does the amplitude go?
Uh,
And what
well,
was our amplitude was what?
our amplitude was 1.
No, there's our amplitude
Oh,
right
right.
there.
Oh, that was yes. So it's 3. We put 3 at the front.
Yeah, so it looks like we do that. Now we just got to figure out if there was any shift here. So if I look at my drawing over here, a cleaner drawing.
Looks like a big shift.
No, hang on. So if I look at a clean drawing, just be careful. Hang on. You can shift almost any thing if you want, but where does this normal one start?
This normal one starts
The green one.
Starts at 0.
0, 0, right?
Yeah.
So it's a 0x value. That's the translations left and right are x. Where does this red one start? It looks like it also starts right at the axis, doesn't it?
Yeah.
So did it actually go left or right from the x?
No, it didn't.
So it looks like there's nothing there for that, correct?
Correct.
Let's go look at your green graph now and see if you got it. So we're just going to focus on the green graph. compared to a normal sine graph. All right, so there's the normal one. So let's go look at our graph and see what this point is. What is this point right here? If this axis is -2, what is this point right here?
It's minus. Oh no,
All
it's
things have x comma y.
0, comma -2.
Okay, let's see if we got it. Did we?
Yes.
Okay, let's go look at our max value up here. Our max value appears to be right there. What's the coordinate there?
The coordinate there is
Remember each box.
180
Yeah.
and
Oh, nice. 180.
1.
180 comma 1. Let's go see if we got it. Okay, I'm going to get rid of this. We don't really.
I just saw it.
We don't really need this. Yeah, there we go. Did you get it?
Yes.
All right, let's go back to our drawing. Chances are if you got the quarter mark, the rest must follow. Let's look at this point, though. What is this point right here? Looks like it's right there. 1 squared to the right of 270.
Is 90. 270. So 270 plus 90. Yeah, so 360 and -2.
Comma -2. Let's see. I got
Yes.
to put the right axis
I
in
know
there.
it's gonna be there.
And it should be right there. Did you
Yes.
get it?
Yes.
So notice that the halfway point is half the period in this case. What do you think our min point should be, just for shoots and giggles? Right here. Looks like
Our
it's...
midpoint is.
Oh, sorry, min point. Min point. Looks like it's what?
Didn't we already figure that out?
Well, tell me again. It's right there.
Okay, -5.
Yeah, but that's just the y value. What's the x value?
X value.
All
is...
points have x comma y. All points. And soon z.
Okay, 270.
No, you
So
got the 5.
No, I'm counting.
You don't. It's right there. It's right visible. Don't have to count.
420.
It's right there. It's right on this number right there.
Oh, I'm blind. Okay, 540.
540 comma what?
540 comma -5.
Yay, let's see if we got it. Did you?
Yes.
Did you correctly transform that graph?
Yes, I did.
Let me show you another way to transform that graph. You tell me what I'm doing here. Okay, I'm going to turn off the green graph. Tell me what I'm doing here. G of x is equal to 3 times f of x, half the x, minus 2. What did I do here? What did I tell Desmos to do?
Let's see. F of x equals sine of x. Let me see this.
Yep,
Okay,
so I defined,
so
you're right, I defined f of x. And then I said g of x is equal to...
Yeah, I know. Let me see
I
this.
know, I'm just...
Okay. Y equals this. And set y. Okay, that's not relevant.
Notice I don't see the word sine in there at all. There's no sine, but I do see that instead of sine.
Yeah. Yeah, I think I know what you told it to do.
What did I tell it to do?
Because you said f of x equals sine of x, there's no need to put sine.
Yeah, I told g of x to take what and apply these transformations to?
To the original graph.
That's right. I said grab f of x, whatever f of x is, doesn't matter what it is, and apply these transformations to it. I put this half by the x because I wanted to make a period of 720. I put this 3 in front because I wanted to stretch it by 3 and create an amplitude of 3. I put this -2 here because I wanted to create a new axis of -2. But guess what? No matter what is there for f of x, even if f of x is equal to the square root of x, it will apply these transformations to it. So the blue is the original graph, and look, the g is the transformations applied to whatever I told it f of x was. So even if it's 2 to the power of x, suddenly my y, my green rather, is a transformative tool. Take whatever f of x is and apply these transformations, and that's my g of x. Does that make sense?
Right. Yes.
And that's what you'll see like this all the time. You'll see it like this. There's no sign in there, but there is an f. And that's saying take the function f of x and apply these transformations and call it a new graph. In this case, they got lazy and they called it y. But you'll also often see g of x, or a new function. Yes or no?
Yes.
What do they want you to do here? They say, here's the
I'm going
point
to
on this graph. And they say what? Determine.
determine the corresponding coordinates of this point on the graph of
So what would you
whatever
do?
this is.
What the hell? What would I do to it?
Determine that. I feel like I know what to do, but the way they said it
Yeah,
is
so let's just
weird.
go slow. We're working with one point, aren't we?
Yeah.
What point are we working with?
2 and 3.
Which one's the x and which one's the y?
2.
X, y.
Oh, wait.
What
I
are
think
the
I know
y
what to do. I know.
What are the y
I know what
transformations?
to do with
I know,
this.
but I want you to list me the y transformations.
The y transformations are -2 and -4.
Yeah. Y's, which one's what? What is the -2?
-2 is the vertical stretch and reflection in the x-axis.
Right. So it is a stretch of 2 and reflection in x-axis. And what's the -4?
4 is where it moves down 4 units.
Shift down vertically. Well, shift vertically. Yeah, shift down 4. So, what would now be my mathematical applications? In other words, what do I do to all my y values to create that?
Multiply by -2
Multiply.
and subtract -4.
Yep. So do that for that y value they gave you.
Okay. 3 times -2 is -6 -4 is -10 is the y.
Okay, that means my new y value is
-10.
So I should take my -10 and put it right there. Now we got to do the same
And
thing
for the x,
So
I think I know what to do for this one also.
Okay.
Yeah. I have to do 2 times 1/2.
Okay, so let's describe the transformations first in the wordy way they like. Yeah, I know. I'm with you. I don't agree. I don't think it's fun. Compression or stretch?
It is a compression.
It is a compression by a factor of what?
2.
Hang on, sorry. It is not 2. Try again.
Oh. Wait.
Did you say compression or stretch? Sorry.
I said compression.
My bad. You are correct. Of what? I am wrong. You are correct because you like to hear that. Go.
Compression of factor 2.
Nope.
A factor 1/2.
That time I got it right.
Perfectly balanced as all things should be.
Yes, you're correct. Now, what is any other x transformations?
Any other x transformations? Yes. 5 to the left.
Okay, how would I apply that?
So that means we should subtract 5.
No, you always do your multiplications first. There's a multiplication here. Right? There's a number.
Okay, mathematically we should do 2 times 1/2 and subtract 5.
Nope. Try again. You've already defined what your compression is actually. It's not 2. So you take
2 times
you're doing the
1/2.
number. I want you to do take all x values. Why? Because there'll be more than just one x value in the future. Multiply by what?
Multiply by 1/2.
Yeah, and then
Subtract 5.
okay. And you are correct. We would take 2 and we would multiply it by a half and get what?
And we would multiply by 1/2 and get, let's see, 2.
2 divided by 2.
Let's in my head real quick.
Yeah. You're making it too hard on
1
yourself. Yeah, it's 1. And then I subtract 5. 1 minus 5 is
minus 4.
minus 4.
So
So
that means our new coordinate is minus 10 and minus 4.
always go x,
4
y.
minus 4, comma, minus 10.
Always go x, comma, y. Now, I know you say, well, why are we doing the y first? Because the y's are easy. And when you get the y's down, it helps you get the x. So that's what they want you to do over and over again here. What are they doing here? They give you a whole bunch of order.
They want me to do the same thing, but with more pairs.
What do they want you to do right there with this one?
They want me to.
Is that a y or an x transformation?
It's a y
Yes,
transformation.
and y's are as you see, they do as you see. So what do I do to all my y values?
Take all the y values, multiply by 2.
Excellent. Any other things in this?
No.
Okay, what's going on here?
This is an x transformation.
And what does it do?
It moves to the right.
So I do what to all my x values?
So that means we need to take all the x values and add 3.
Excellent. And what about this?
Take all the y values and add 2.
Why do you think they're doing it step by step like this, and then suddenly they mix it up? Why do you think they make you do this first?
Because it's easier.
One by one, you get to study each transformation in front. So what's going on with this one?
This one you have left slash right, down slash up.
So what would I do to all my x values?
To all your x values for this one, you would subtract. Take all the x values and subtract 1.
That's correct. And what would I do to all my y values?
Subtract 3.
Yeah, so y's are easy. As you see, just x, you just constantly say opposite, opposite, opposite.
Damn x's.
And what do we do with that one?
For that one, we just multiply. No, we add 1.
Nope. Is that multiplying x or is it adding to x?
It's adding to x.
No. That little minus essentially says minus 1 times x. It's a reflection in the y-axis. But what do I do to all my x values when there's a little minus 1 multiplying in front?
Minus 1 multiplying in front. And that. Oh, the opposite, yes.
Yeah, the opposite is a reciprocal of 1 is still 1, so it still becomes minus 1. The reciprocal of minus 1 is still minus 1. So what do I do to all my x values?
You multiply by minus 1.
Yeah, that's it. What do I do to all my x values down in this bottom one right here?
You multiply by 1/2.
Yep, and then what do I do to all my y values?
Subtract 1.
There you go. Why do you think they make you do this over and over and over again?
Because practice equals math.
Practice equals perfect, and if you get it down pat when you come to a test, your score gets higher and higher. What is your goal? Ultimately, to get into university with a good score. How do you get a good score? Do all the homework. The more homework you do, the better your score. What do you think why do you think they move, what do you think the difference is in this question? What do you notice they do in this? In these 6 questions here.
Oh, now they actually got complicated.
No.
Oh, wait. Let me read the instructions.
Okay, fair enough. Let's
Oh, they just want me to list the transformations applied.
Yeah, but let's start with this. What are the parent functions? What's the parent function of this?
Y equals x squared.
Yep, this one.
Y equals absolute value x.
This one.
Sine of x.
Yep, this one.
1 over x.
This one.
2 to the x.
Yep, this one.
Square root of x.
So they're trying to show you how to transform different functions, but the transformation rules still apply. What happens to this one? I won't do them all. What happens to this one?
This one.
There's only
It's
one.
square.
No. That's part of the actual function. You've got to focus on the transformations. The only thing
It
different.
moves to the left by 1.
Yeah, so all my x values, I would subtract 1. This one's outside of the x. It's not inside the bracket.
Vertically stretched by 2.
So I'd multiply all my y values by
2.
Yep. This one, the 3 is beside the x, so there it's multiplying it, but x does the opposite. So what do I multiply all my x?
Multiply by 1 over 3,
Yep,
add 1.
there you go. To add 1 to not my x values, though, to my,
Y.
because it's outside the bracket.
Mhm.
Are all these inside the square root?
Yes.
Therefore, they are all what transformations?
X's.
Yeah, so what happens to all my x's here?
So it's multiply by 1/2 and to add
Yeah,
6.
you nailed it. Now, this one's tricky because they made it a decimal, but the actual decimal
It's just a square root.
No, this is what's the parent function?
Isn't anything to the power of a half a square root?
No, let's slow down a bit. Slow down a bit and go back to the basics. They want you to name the parent function. So how about you?
Oh, to the x.
Yeah, so we're dealing with a growth curve, and now we do the transformations. There's only something beside. What's the difference between this and this? There's something multiplying the x, right? So that's
Yeah.
the same transformation rules. We have something multiplying the x. What's the fraction equivalent of 0.5?
Half.
So we have an x that's being multiplied by a half. What do I actually do to all my x values? I don't multiply by half.
You multiply by 2.
Yeah, so that means I take all my x values from my original parent function, multiply them by 2. Are there any other transformations going on here?
No.
No. So I just take all my values. Can you name two x values for the graph, two xy coordinates for the graph 2 to the x? So the easiest ones are when x is 0.
Oh, I know this.
Yeah, when x is 0 and then x is 1.
2. Let's see. 2 and 4.
Nope.
4 and 2.
No. Stop guessing. I can always tell when people are guessing. So how do you find the y value? If y is equal to 2 to the x, you substitute x up
Oh,
here.
no. Yes. So that means it's 2 and 1 is a coordinate.
Yeah, but you got it. No, so x, I've given you x. There's no 2 anywhere in the x. What's the x? X is either 0 or 1. So what's
So
0,
that's 0.
comma,
1.
what? Say it again.
0, comma 1.
Yes. Now when x is 1, over here, what is
1, comma 2.
You'll notice that for exponentials, it's always 1 comma the base, whatever the base is, and it's always 0 comma 1. So 1 comma 2, we have 2 points. Over here, we've determined that we have to multiply all our x values by
2.
So multiply this x value by 2.
0.
Okay, so all that happens is it becomes 0 comma 1. Nothing happened to it. Multiply these x values by 2.
2.
Comma what?
2.
Yeah, the y values didn't change. So that means if I take the parent function of that and apply this to it, hang on, 0.5x, or we'll just use half an x. It should do it for me. So there we know 0.1 stayed the same. And let's find out where 1, look, this one is 1 comma 2 up here as soon as I get there. And this one on the parent graph is here. We'll do 1 comma 1. We'll do 0 comma 1 to show that they share that point. 1 comma 2 to show you on the new graph, on the original. And 2 comma 2 to show you the transformation. So I'll turn off the purple. Would you agree that this is the original graph, the parent function?
Yes.
Would you agree that those are the 2 main points?
Yes.
Right, so we'll just label them all. All right, we'll actually label all of them so that we can see it. Now we're going to turn on the main graph. Ready? Or the transform graph. Would you agree that you transformed those points correctly?
Yes.
The x value got multiplied by 2 and stayed the same in this case. Now, since you know what a growth graph looks like, you could just kind of sketch through those points. But you must know what a growth graph looks like in order to sketch it. Make sense?
Yes.
Right. So notice that they do indeed want you to graph eventually, and the best way is to take 3, in this case 2 is easy, 2 or 3 points and transform them. Then they want you to go back and spot any domain and range adjustments. Then they want you to graph it and apply an adjustment to this one. Woo, it's endless.
I'm beginning to hate
graph, and they want you to graph. Now, some people say functions 12 is harder than calculus, and mostly it's because the graphing, and people get tired of graphing. But notice how much time they spend on graphing, quite a bit. Let's have fun with inverse relationships instead. Let me ask you if you remember, and your homework's going to be transformations again, and it's the weekend, so you get a couple more. Let me ask you if you remember how to. This is a line, wouldn't you agree?
Yes.
How would I find the inverse? What's the first step? Do you remember?
X equals 2y.
Yeah. Now,
That's the only step I remember.
then you must. You're right. The first step. Swap. And sometimes you have to, if it's f of x equals 2x, you have to put in y is equal to 2x and swap x and y. And you get x is equal to 2y. The second step is follow the reverse rules of BEDMAS to get this new y all alone as y is equal to something. So if this is my new formula for my inverse, my new formula in red is x is equal to 2y. How do I get it down to y is equal to something? How do I get y all alone here?
X minus 2.
No, because this is multiplying y, so I would never subtract 2.
Oh, you divide. You
So
divide
I
by
have
2.
to divide both sides, don't I?
Yeah, divide both
So I
sides
get
by 2.
x divided by 2 and 2y divided by 2. What happens to this here?
Cancels.
Yeah, so have I now got y alone?
Yes.
But I don't like that x over 2, so I'm going to write it as a half times x. And you might say,
Why?
Yeah, hang on, I'll show you why. So I got y is equal to x over 2. But as you've seen, have you ever seen it written, a line written like this? Sometimes, I guess. But what we prefer is just to say, well, that's the same as a half times x, because that way I can see the slope is clearly.
Yeah, but how they know the X is 1?
Oh, because 1 is a multiplier always in front of this. There's an invisible 1 right here. And I can see that the fraction is right there. So I can easily write it as 1/2 over x. And if you want to test yourself, what is x over? It's over an invisible 1. What's 1 times x?
X
What's 2 times 1?
over 2.
Yeah, so I can see that this here is the same as writing it like this. The reason I write it like this is so I can see the slope on this new one is clearly a half. So let's see if that you've discovered an inverse.
Which is also not a function, by the way.
Inverses of lines are always functions.
Uh,
Yeah, inverses of things like parabolas aren't. So here's 2x, and let's call it f of x. And we claim that the inverse g of x is equal to this, correct?
yes.
Now, all inverses reflect through this line called y is equal to x. What that means is if this line was staring at the blue mirror, it should see a dot the equal distance away on the other side. Let's test that out. What's the coordinate here?
5 comma 2.5.
An inverse, I just swap the x and y's. If I swap the x and y's here, I should find the
It should be 2.5 and 5.
right there on the other side of the mirror. So there it is. Right, notice that it's right across the mirror from that point.
Yes.
What about this point here? What's this coordinate here? 3 comma.
3 comma 1.5.
What should I find in the red line?
In the red line, you should find.
The blue is just the mirror, so I'll just turn.
Oh, right. 1.5 and 3.
You should, if I find 3 comma 1.5, I should find
1.5 comma 3.
Ooh, there it is. And notice it's on the exact same distance straight through the mirror. They're straight through the mirror. That's where those 2 points are. What about a point little like here? What's that point?
1 and 0.5.
1 comma 0.5. What should I find in the red line?
In the red line, you should find 0.5 comma 1.
Yeah. By the way, the domains and ranges switch on inverses too. But in a line, it doesn't matter. And some inverses are still functions. For instance, are both those still functions? Is that red line a
Yes.
function? Is that green line a function?
Mhm.
So not always true that inverses are never functions. Sometimes they are. Let's work on a more complicated inverse. The square root. Let's find the inverse of this. What's your first step for inverses?
The first step for inverses, let's see, x equals 2y
Yeah,
square root.
yeah. X is equal to the square root of 2y, like this. Now, there's two things going on. I'm trying to now get it to the stage of y is equal to. But there's so much going on here. I've got the square root of 2y. What do I have to do to start unraveling this? So the
You think you,
huh?
I think you have to square both sides.
Yeah. When I square the right side, what happens to that square root?
Uh, Square root cancels.
Yeah, anytime you square square root, it cancels. That's why we squared it. So far I got this.
So x squared equals 2y. And then we need to divide each side by 2.
Yeah, so if I do it on this right side, it disappears. If I do it on this left side, I got this thing. And you know I don't like writing it like that. So I actually write it as y not is equal to x squared over 2. But what do I
Y
write?
equals 1x squared over 2.
No, I don't like to write it like that. So I would actually write it like this. Why? Because then I can see the transformations clearly. I can't see the transformations clearly if I write it like that. But I can see it if I write it like this.
Oh, yes.
So let's see if that's true. Let's see what happens. So here's our main one, and here's our inverse one. And by the way, how come I have two? How come I got a parabola, but clearly this is a half square root? Well, we must stop ourselves and go back. What is the no? What is the domain and range of this? Well, that's not going to have too much factor on the domain. What is the domain and range of the normal parent function?
The domain and range of a normal parent. Oh, of that, yes. It is x greater than or equal to 0.
Yeah. So it looks like we have a restriction
And
that
then
x
same with y.
x is bigger or equal to 0 and y. So we have a restriction, right?
Hmm.
Now, what do you know about inverses? Do you remember what I said about inverses? The
They're the opposite.
Yeah, so that means the domain of this one must become the range of that one. So that means the
Same.
domain of this is x is bigger or equal to 0. And the range must be also swapped. You must swap their so y must be bigger. It happens to be the same thing because they had the same restrictions, right?
Hmm.
So that means over here, when I redo this inverse, even though this is the correct inverse, I must apply the same restrictions because the square root function didn't have the same x values available. So I must, in the bracket, say x is bigger or equal to 0. And now it looks like I have a correct inverse. And you might say, why? And that's because the only x values and y values available on this one are the only ones that can appear on the inverse. So that means only these x, y values can come over here. Yes, if we did the pure inverse, we would end up with this on the bottom. But that's not what we're working with. If that was the case, yeah, we could find the whole parabola. But that's not the case. We were working only with this top half. Therefore, we must only have the same restrictions on this bottom, on this inverse. Does that make sense?
Yeah, that is a beautiful inverse.
Isn't it? Let's draw the line y is equal to x and show that it does indeed mirror. It didn't that time. Let's see. Oh, because I forgot the 2 there. There, now it's a beautiful inverse. Look at that symmetry. This is the original.
It actually looks 3D.
Yeah, let me find a point here. Why do they share this point? Why, when I turn on the inverse, do they share this point?
Yes.
Why?
They share this point because they're mirrors of each other.
Yeah, don't you remember what we did? We swapped the x and the y's.
Yeah.
Tell me the x and the y there. What's the x and what's the y as soon as there?
Two and two, two and two,
If I
because they're
swap it,
mirrors.
if I swap
Mirrors.
it, it's the same coordinate, isn't it?
Yes.
Okay. All these things help you understand. So if this is a point on, let me find a clean point. There's a clean point. 6 comma 3.5. What should I find on the other one? Actually, that's not
6 comma
that,
3.5,
yeah,
so you should find 3.5 comma 6.
let me take this one. That one wasn't clean. 8 comma
Yeah.
4. 8 comma 4.
8 comma 4, so 4 comma 8. I think I get this.
Yeah. So there 4, it's way up here. There it is. Makes sense, right?
Yeah.
Notice that through the line, they are straight through. If you look straight at the blue line, they are straight across from each other through the blue line. Even when they swap. So the black line suddenly goes below the blue line, but the red line goes above the blue line. And this point is exactly opposite this point through the blue line. Okay?
Yeah.
Inverses are fun, so I'm going to give you an inverse to do. Now, let me look at the mathematics of this. How do I inverse this mathematically? X is equal to the square root of 2y. Well, you can always tell the story, and you have to tell inside. You treat square roots like brackets. What's going on here to y? First, it's multiplied by 2, and then it's square rooted.
Mm-hmm.
To tell the reverse story, I take this story, and I have to make my number 2 my number 1, and I have to do the reverse of a square root. What's the reverse of a square root?
Reverse of a square root is a square.
I must square both sides.
And then you get x squared.
Wait.
And the right side cancels out, so you're
And
left
then
with
I
x
must
squared
do
equals 2y.
I must do the opposite of this now as my second step. So my
Yeah.
second step, what's the opposite of multiply everything by 2?
Divide each side by 2.
Great. Now I have instructions. Now I have instructions for this. So I want you to follow those instructions. What's the first instruction, number 1?
The first instruction is to
It's in green right down here.
yes, square both sides.
Okay, that's what you did. You knew instinctively to square 'em. And
Wait, didn't we do this already?
I know, but I want you to show how. I want to show how to decipher it because it's going to get more complicated. You describe the bed mass operations on this side, and then you reverse the order and reverse the mathematical process. So when you square both sides, what happens? You got rid of the square root. Follow
So
step
now we divide each side by 2.
2. Right,
Right side cancels.
right. And then you unraveled it.
So then we're left with 1/2 x squared.
Yeah. And you found a mathematical explanation of the bed mass order, and then you've got to reverse the order and do the opposite mathematical function. It's kind of reverse bed mass, right? Now, before I let you go, this is the reason I wanted you to do that. I'm going to give you a complicated one.
X.
Yeah.
And then I can write an entire essay about the story of X.
Good. You have the whole weekend, so that's good.
Once upon a time, X was being bothered by this.
All right. So now if I swap X and Y here, if I swap X and Y, I want you to help me tell the story of Y. And in BEDMAS, you have to go inside the bracket first in BEDMAS, because BEDMAS says what? Bracket, exponent. And by the way, technically that there's an exponent there, but we have brackets first. The exponent is a square root. What's the actual exponent?
To the power of 2.
No, a square root is actually to the power of a half. That's what it's actually an exponent. It's just written as square root. Don't you remember?
Yeah.
4 to the power of a half is the same as square root of 4 is equal to 2. So we can see that a square root is actually an exponent. But we have to do brackets first. Right? Does that make sense?
Yeah.
So tell me everything that's going on inside. If this is Y, so I'll just make it a bit cleaner. If that is Y, tell me everything in BEDMAS order
Okay, so
What is how
3 is being added to y.
3 is added to y. That's number 1. Yep. What's next?
This entire square root is an
Now there's
actual.
something inside the square root that's being done first because the square root counts as a bracket. So
Oh yes, 4 is being multiplied to that bracket.
yeah, everything is being multiplied by 4.
Um,
What
and
now?
then
You can go
5
out.
is also
No,
added
no,
to the bracket.
now there's something between the 5 before you ever get to the 5, and that's right this thing. So if we look at it as a bracket,
2 is multiplying the square
no,
root.
no, 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 no. So this square root is like a bracket with a half over it before you can ever get to -2 or +5. BEDMAS says exponents come first. BEDMAS says brackets come first. That's why we didn't get to the exponent first. You did the brackets. You said, well, inside the bracket, inside this bracket, there's another bracket. And you said, okay, well, the bracket that comes first is 3 is added.
Mhm.
Then you said the next bracket was 4 is multiplying everything. Now,
Mhm.
now you finished those brackets, didn't you?
Yeah.
In BEDMAS, what comes first? Well, we did all the brackets. Do I see an exponent?
Yes.
Yeah, that square root is technically the exponent of a half. So since that means everything is being square rooted. Right?
Mhm.
Now you've eliminated this, and you've eliminated this. You're now allowed to go past BEDMAS to the next parts. What's the next
Okay.
parts?
-2 is multiplying the square root.
Yeah. Do you understand why that other stuff has to come first?
Yes.
Because it's BEDMAS. So now everything is multiplied by -2. Now there's only one thing left.
5 is being added to the.
Right, 5 is being added. Now, you tell me the reverse of this story. You got to start with 5 and change the mathematical process.
Subtract 5 on each side.
So our first step is we're going to be subtracting 5 on each side. Right? What's your next step?
And we're going to divide by 2.
No, almost divide everything by. Not
Divide
2.
everything by -2.
Minus,
Oh no,
yeah, no, it's minus.
yeah,
2.
-2. Yes,
Yeah,
yes.
you don't change the signs, just the multiplication, just whether it's multiplied or just the mathematical. What's our next step?
Then we're going to square everything.
We're going to square both sides. What's our next step?
Divide by 4.
Yeah, actually, I meant to say multiplying everything. Divide by 4, so it's multiplying.
Yes, 4 is multiplying.
And so now what's your last step?
Subtract 3 on both sides.
Yep, subtract 3 on both sides. Let's see if that works. Follow this now for this formula. I'm going to write it out clearly. X is equal to -2, and I'm going to use it like this. I'm going to just put a half there because it's really an exponent of a half. And if you like, I'll put the square root.
Please.
All right, there we go. I'm busy. I'll be out there soon. So follow the order.
All right.
What do I do first? I'll tell you what.
Subtract
That's going to be your homework.
Okay.
Okay, and I'm going to give you a few transformations. And did you page through the math book?
Yes, I paged through some of the math.
No. Did you page through the whole math book?
No, not the.
I don't want you to read it all. I want you to race to the end, the title of each chapter and the end of each chapter, and then move on. That's your other assignment. It's been the third assignment. Bye-bye.
Okay.
Take care. Enjoy.
You too.
Enjoy. Love math. Math is wonderful. All right, Mom.